Okay, more fun with Ka and Kb. When we last left off, we were doing a couple of Kb problems, and we saw that they were done basically the same exact way. The only difference is that you have water in the equation, but that's a liquid, so that doesn't really change anything with respect to the actual algebra involved. Okay, so now we're actually going to put it all together. And I want you to look at these two reactions. And I know that one is an Arrhenius reaction, one is Bronsted-Lowry, but hopefully you can see that they're actually the same reaction but in different directions. What I'm saying is the first one here is NH4, okay, NH4, the acid, losing its H and making NH3 and H. And the other one is actually the opposite. It's the same reaction in reverse. Okay, so we have NH3 gaining an H from the acid, which is water, and creating NH4, okay, with the OH. All right, and our definition of an acid and base is preserved. We're giving off both H and OH. And note that I have both the Ka and the Kb represented below, and that should make complete sense as well. Okay, so what does this mean? Well, remember what happens if we do a stepwise reaction. Okay, it's almost similar to Hess's law in a way, when we have multiple reactions that we're going to add up. Okay, and this is true for all acid-base reactions and the conjugate. What I mean by that is and the reverse. Okay, when we take the summation of our Ka and Kb reaction, look what happens. Okay, we add those up and we get to cross off things that show up on both sides. Okay, just like Hess's law, or just like when we were adding up double equilibrium problems. And you see that we're actually just showing the dissociation of water. Okay, and this reaction had, the first reaction had a Ka and the Kb. Okay, this K would equal Ka, let me see the K, Ka times Kb. Okay, in this K we already know is water. Okay, this is another example of how we can use the Kw of water in order to figure out the acid or base dissociation constant. Okay, it's true for all reactions. Now you can't just pick any Ka and Kb. Okay, they have to be the same reaction in reverse. What I mean by that is one would be the acid reaction, one would be the conjugate or the reverse, or vice versa. Okay, so what we're trying to say here is anytime I give you a reaction, okay, you can also rephrase it as the conjugate by taking the K. You know, if I give you an acid reaction, you could also write the Kb reaction and have an appropriate number for it. Okay, and so you know, if I give it to you one way, you can figure out the opposite direction. All right, now we can actually take some natural logs, or I'm sorry, some logarithms of this equation. You're going to see that they're doing the same work that we already did here, showing that this is actually Ka times Kb. And if you don't believe me, you can actually substitute the terms in and get the cross out. Okay, like terms on the top and bottom, cross out, and you're left with Ka times Kb yielding Kw. Okay, this is kind of the derivation of that. All right, but if we take the negative log of everything, all right, we knew that this top equation was equal to 1 times 10 to the negative 14. Okay, but if we take the natural log of both sides, if you remember correctly, we left with pH plus OH yielding 14. We already had that one, but now we're going to take the natural log, the negative log of the Ka's as well, and you end up with this new equation that's on the bottom. Okay, We took the negative log of H and we got pH. We took the negative log of OH and we got POH. Now we're taking the negative log of Ka and we get pKa, negative log of Kb and we get pKb. Okay, and that equals 14. 14 is the pKw. Okay, I don't think we used that term before. All right, so this might actually be useful. It's another way to express Kas or Kb. Okay, and we'll actually start to get some formulas that actually rely on Kas and Kbs. Erasing. Okay. I'm sorry about this. All right, an example of this would be here we have the acetate. All right, we have the acetate breaking up, acetic acid breaking up and giving off its H. And the flip side would be the acetate ion reacting with water in order to create OH. Okay, it's the same reaction, but now it's the basic version of that reaction. And as long as I have a Ka or a Kb, I can figure out the other one. Now, I don't want you to think that this is just the inverse. Okay, a lot of us would say, well, wait a second, isn't that just the reverse? It's almost the reverse, but not quite. And what I mean by that is the reverse was the inverse. Okay, if you remember, if I gave you an equilibrium reaction to go backwards, you just take the 1 over K. And that's true, but this is very similar to the reverse, but it's the reaction with water is a little bit different. You can't just do that to do this. What I'm saying basically is that these are different reactions. Okay, so it's not just the inverse to go backwards, because that's not exactly what's happening here. It would be the inverse to go backwards if it was the same players. Okay, so what I'm saying is, for this example with the acetate ion, 1 over Ka would be this reaction. All right, with the acetate ion. But note that this isn't the same exact reaction. It's very similar. Okay, it's very similar, but there's no stealing the H off of water. Okay, water doesn't have to be the acid in the green example here, because you already have an acid H to react with. Okay, so this reaction would be the inverse. But the reaction above the line here with the acetate ion reacting with water is not the inverse of 1 over Ka. It's actually the Kb. But no fret. I mean, we always have the Kw. So if we always have the Kw, we'll always be able to have the Kb. Must be an easy way to erase. Somebody help me. All right. Moving onward. And you can see that they just did the math again to show the, if you do the math on this, that it's going to be the water reaction, K times Kb equals Kw once again. All right, I don't think I give you any questions on actually solving from Kw, I'm sorry, Ka from Kb or vice versa. It will be in our homework though, so you'll have a couple examples of that. Okay, we've already talked about this, so we should be able to cruise fairly quick. Okay, we're talking about acid bases of salts. All right, what I'm saying is analyze the anion and the cation to find out where these ions came from acid base wise, and using that weak makes something, strong makes nothing scenario, figure out if you actually have a acid or base. All right, so you can actually think of both the cation coming from being a conjugate of a base and the anion being a conjugate of an acid. By the way, the salt again means any ionic compound is a salt. All right, NaCl. NaCl is completely neutral. And in class, we were only dealing with the anion. The anion is neutral. It doesn't have any acid-base characteristics because it's coming from HCl, which is a strong acid. Well, as it turns out, you also have to analyze the Na. And the Na comes from, the sodium comes from, you could say, NaOH, a strong base. So using that whole strong makes nothing, weak makes something argument, the strongs make nothing. NaCl, if you dissolve this in water, does not change the pH whatsoever. Okay, it's neutral. It's not, doesn't have any acid-base characteristics whatsoever. So it's the same thing we did in class, except now we have to analyze both ends. All right, the anion and the cation. NaNO3, same exact situation. Strong, strong, which means that this one is also, all right, neutral, or no AB characteristics. All right, next up. Sodium acetate. Okay, now we're talking here. Now we actually have something we can work with. Sodium, again, the alkali and the alkalines you can visualize coming from the hydroxides, which are strong. The acetate's coming from acetic acid, which is a weak acid. So sodium acetate, all right, will actually have basic characteristics. So it's a base. It's a base only because of the anion. The sodium does nothing. So overall, sodium acetate is a base. All right, it's also the flavoring in like salt and vinegar potato chips is sodium acetate. Non-toxic. All right, next up. Guess we're not doing more of those. Those are kind of fun. Hydrolysis. We've seen this word now a few times. All right, hydrolysis means basically, hydrolysis means a reaction with water. Okay, if you react with water and make H or OH. Okay, we've been seeing a lot of hydrolysis with our anions. Okay, our anions, in this case, like our acetate ion, which is a base, is going to react with water to make OH. We've seen many times now the NH3 reaction reacting with water to make NH4 and OH. Those are hydrolysis reactions. Okay, not so bad. Now, we've said this once before. When you have something that's a polyprotic acid, like in this case H3PO4 that lost 2 of its H's, it's amphoteric. Remember what amphoteric meant was it could be either an acid or a base. So my H3PO4 negative 2 can either go, lose its H and become an acid, or it can pick up one of its lost H's, or any old H, and in that case it'd be a base. So it's completely amphoteric. Okay, here's a pretty good question here they have for us. I want to know if the solution of Na2HPO4 is acidic or basic. Acidic or basic. Okay, and to figure this out, we have to basically compare K's. Okay, we just said HPO4 is amphoteric. It can pick up an H and become H2PO4 ion, or it can lose its H to become the phosphate ion. And we actually have both of those reactions given here, but not totally. Okay, losing its H would be this reaction to become phosphate, and there's a Ka for that because that's an acid. I give you this one, but this reaction is almost meaningless on its face with a Ka. We don't want this reaction. Okay, we have to do some math here and figure out what the opposite is. Okay, and when I say the opposite, I mean the Kb of this reaction. The Kb reaction of this reaction is the HPO4 minus 2 plus H2O. okay, yielding H2PO4 negative ion. Okay, and that's going to be our comparison. Our comparison to be between this reaction and this reaction, because HPO4 can lose its H, or HPO4 can gain another H. And we need to know what the KB is. And they didn't give us any problems to actually do the changeover from K to KB, but now we actually have one. All right, in order to find out the KB is, I'm going to use this property. Okay, remember this one, Ka KB equals Kw. All right, I believe that's on our equation sheet. Kw we know is 1e negative 14. So in order to figure this out, it's going to be 1e negative 14 divided by 6.2 e negative 8. And I just did that, and I received an answer of 1.6 times 10 to the negative 7. Okay, 1.6 times 10 to the negative 7. So what does that tell us? Basically, we're saying it's basic. Okay, so in this scenario, when you're just dealing with plain Jane water, HPO4 ion, hydrogen phosphate ion, is a basic anion. It has more of a tendency to go back to the dihydrogen phosphate ion compared to its tendency to lose its H. All right, and I think they did some the math on the following pages to do the same thing that we just did. All right, looks like they're doing the same thing here with the Kas, finding the Kb. All right, they found the same value to the negative 7 and also proclaimed it to be basic. Okay, so again, anytime you have a Ka, you can figure out the Kb from that characteristic. Again, we're talking about the conjugate. And again, I can't stress this enough. We're not saying the reverse reaction, because that's inverse. Taking the acid or the base reaction conjugate is not just the reverse, even though it looks very, very similar to it. Okay, first of all, the cations of the alkalis and alkalines do not hydrolyze in water. So what I'm saying is, and this is something we've covered now several times, they don't react with water. They don't have hydrolyze, meaning producing HOH. They do not influence the pH. They're neutral. Why are they neutral? Again, because they come from strongs. Okay, Na would come from NaOH. If you had something like magnesium, it would come from MgOH2. All right, so we're back to this a little bit. We can predict the overall acid-basic character based on the strength of the conjugates. Okay, and that's particularly true now. Even if we wanted to do it with numbers, we have this whole Ka-Kb relationship. So we're going to go back and do a very similar exercise that we did earlier. And we've already talked about both of these, NaCl and NaNO3, that both the cation and the anion came from strongs, so they're both neutral. Okay, moving forward. And there you go. Strong base, strong acid is the conjugate parts. Okay, Na came from NaOH, NO3 came from HNO3, and no hydrolysis happens. So NaNO3 is a neutral salt. Okay, now what about this one here? NaClO. HClO is a weak acid. Okay, so we have to analyze where they came from. HClO is a weak acid. Na came from NaOH, strong. A strong base. So the Na is meaningless. The ClO does indeed have basic character. So the overall salt is basic. Okay, so I'm basically analyzing from the origins of the ions to figure out where they came from. Okay, and then I can figure out what the pH would be, or whether it be acidic or basic. All right, moving forward, another example. sodium acetate. Okay, I feel like we've already talked about this one. Again, the Na came from NaOH. The acetate comes from acetic acid, a weak acid. So it's a basic overall. How about this one? A weak and a strong. NH4Cl. NH4Cl. The Cl came from HCl, so that's nothing. The NH4 came from NH3. Okay, so if I highlight this NH3, which is a weak base, HCl, which is a strong acid. So the Cl character is non-existent, it's neutral. The NH4 character is overall acidic. Okay, so the overall salt is acidic. AlNO3, again, HNO3 is strong, so that's insignificant. You could visualize the Al coming from AlOH3. And even though there's no hydrogens in aluminum, because it's coming from a weak base, okay, just because it's a hydroxide doesn't mean it's strong. Remember, only the alkali alkalines. The aluminum coming from aluminum hydroxide would be acidic. Okay, so that's two examples of the acids. All right, and you can probably visualize what we're actually going to talk about next. What happens if we have the scenario of course, we already talked about this one. Skipping ahead, going quicker. Okay, this is the scenario that you've thought of, I'm assuming, is weak and weak. NH4, C2H3O2, ammonium acetate. Okay, so acetate came from acetic acid, vinegar. Ammonium came from NH3. Weak and weak. Weak makes something. Okay. There's no way for us to tell without numbers who's going to win the battle. What I mean by that is that when you're plopping in ammonium acetate into a beaker, you're basically adding, you're basically adding an acid and a base. This is the acid, the NH4 plus 1, and then this is the base, the acetate ion. You're adding both an acid and a base. So what happens to the water? Is the water going to become acidic or basic? Well, you have to actually have numbers for this. Okay, you're going to have to, it's going to basically depend on how acidic and how basic they are. So you're going to have Ks and Kbs. The same holds true here for my iron carbonate, or carbonic acid, and iron hydroxide. We're going to say it's iron 2 because it's iron 2 here. And again, we're coming from weak and weak, which means that they do have character, and that would depend on the relative size of the Kas and Kbs. Right? So you don't have an outright determination. Okay, not enough information. Typically, these questions show up on the multiple choice, and the multiple choice wouldn't give you a scenario like this. It would be a scenario where you would be able to tell and would be able to give me a definitive answer. Okay, so again, you're going to compare the K and the Kb, and whoever's bigger is the winner. My missing character here is equal. When Kb and Ka are equal, then it's nearly neutral. I think you'd actually be fairly safe to take the nearly out and just call it neutral. Okay, I'm going to actually fix that right now. Looks like that. All right. In fact, I'm going to call it neutral myself. All right. So you're determining both the Ks and the Kbs of the cation and anion to figure out who's actually the victor. All right. NO3. Well, we already talked about NO3 coming from HNO3, so it doesn't do anything. So it's a no reaction. So if they wanted a net ionic for the hydrolysis reaction between NO3 and water, there you have it. You don't get one because there isn't one to write. NO2, on the other hand, is different. NO2 came from HNO2, which is not one of our 6 or 7 strong acids. Okay, nitric acid is a strong acid. Nitrous acid is not, it's weak. Okay, so you can write the hydrolysis reaction just so show what actually happens here. Your hydrolysis reactions are always going to have the 4 components with water here in the middle. And you can see that it's indeed a basic reaction because I'm reacting with my water and giving off OH. All right, ammonium, what happens to ammonium? Well, it's donating an H to water. Okay, so the NH4 is the acid, and that makes it acidic. It's hydrolysis reaction. If we're going to predict on these 3 chemicals to find out, what their acidity and basicity is by a prediction, we're going to look at this and we're going to see that Ki is coming from KOH and HI, strong and strong. So we're going to say that it is neutral or no characteristics. HI's carry over to the second one. That's strong, so that one's out. NH4 came from NH3, a base. So this one is acidic. This was neutral. Potassium acetate, KOH, which is strong, means that's nothing. Acetic acid came from the acetate came from acetic acid, which was weak, makes this a base. Okay, next we're going to start learning if we could somewhat predict the strength of the acid based on the actual structure of the molecule. Okay, it turns out that it is a repeating pattern. We can actually start to look at the way the acid is put together and predict or compare acids to tell who's actually stronger based solely on intermolecular forces. And that's what we're going to be doing now.